Welcome. Today's lesson is entitled Compositions of Functions Day 2. We'll take the opportunity today to solidify some of the skills from the previous lesson and then also maybe expand to a couple other ideas dealing with compositions. So why don't we start with a fairly artificial investigation here, but good one to get us sort of thinking back on the track of compositions of functions. So here we go. It says you're buying a car with a price of X dollars and two options here. Option A, you're going to receive a factory rebate of $2,000 followed by a 10% discount. Or option B, you get the 10% discount first, then followed by the $2,000 rebate. And I guess obviously the quick first question would be, does the order matter here? Is that going to affect the final price? And how does that relate obviously to our compositions of functions? So let's start it out. A and B kind of work together here. What we're going to do is to create two individual functions. Then because this is a compositions of functions lesson, we're going to combine them together the way we did on the previous lesson. So here we go. Letter A, write a function f of x representing the cost of the car if just the $2,000 rebate is going to be applied. So let's immediately just start it out here with f of x equals, and the car is initially X dollars. So that is the original price right there, which is X. And I'm going to get a $2,000 rebate on it, which means I'm going to subtract $2,000 from the original price, and that would give me the new price of the car. So original price goes in, I subtract $2,000 from it. When I do that, I get the new price. Excellent, no big deal. Then we go to part B, write a function g of x representing the cost of the car if just the 10% discount is applied. Okay, so let's see how this plays out. We might take this in two steps now that I'm looking at it. So how do I get the new price of the car? Well, I start with the original price of the car, and I'm going to take a 10% discount off of it. So what that means essentially is I'm going to subtract 10% of the original price. So this would be one way to pull this off, and this is unsimplified, by the way, so I'm going to take a moment and simplify this. But that would essentially be the function. The original price of the car minus 10% of the original price. Now I have the new price of the car. Perfect. Now if I do combine these together, because I do see some like terms here, this is a 1x minus 0.1x. So I am hoping that you see that 1x minus 0.1x would be 0.9x. And that kind of makes sense. Think about it this way. If I'm taking 10% off of the price of the car, then it has retained 90% of the price of the car. So 0.9 times the original price of the car, and that would give me the new price. All right, so I have, at this stage, my two individual functions. Let's go with those two right there. Now, let's go back to the options and talk about it in terms of a composition. So which option from the top of the page would be f composed of g of x, and which option would be g composed of f of x? I want you to visualize that without actually doing the math just yet. Let's see if you can kind of pull that off. Which is which? Well, from what I'm seeing, f composed of g of x, so that means I'm doing g of x first, so it looks like I'm doing the discount first, then putting that into the f function, then putting that in and subtracting the 2,000. So this seems to be discount first, then the rebate. And that looks to be option B. Whereas g composed of f of x means I'm going to take the rebate first, and after the rebate, I'm going to get my 10% discount. And if you look, that's exactly what option A states. So I like that, just making that little connection mathematically. The order here in which these two are applied is the distinction between f composed of g of x and g composed of f of x. All right, I'm hoping you saw that piece without actually doing the compositions themselves. But now let's go ahead and do the compositions, I suppose. So f composed of g of x, I might have to go back to my original screen there. But that means just take g of x. So let me go ahead and do that just visually. That means taking g of x, which is this. Hopefully everybody remembers that. That's g of x. That replaces the inputs of the f function, so that replaces that right in there. So this goes right into there. And so I just get, instead of x, that would be 0.9x. All right, so 0.9x minus 2,000. That's option B. And then the other one, g composed of f of x, which option A. And let's just see that play out. So g composed of f of x. So let's see, here's f of x, everybody. So that's this piece right here. According to my notation, f of x replaces the inputs of the g function. So everybody take that f of x, which is this, and bring your arrow in, replaces the input of the g function. So it goes right in there. So I'm going to get 0.9, not times x, but 0.9 times the whole x minus 2,000. All right. That's looking really nice. It says if the initial price was $18,500, which is the better option there. So now I have my input, my original value for the price of the car. If I put that in here for option B, and by the way, I'm just going to, for my purposes, just put that as option B and option A. Put them in, see which is the better. All right, let's do just some very quick calculation on that. So 0.9 times the original value, so 18.5, and then minus the $2,000. There we go. That would be the first. So that was option B. So that was the f composed of g of x. Then let's do the option A, which would be, let me make sure I get that right for you. And 0.9, there we go, minus the $2,000. And if you happen to notice here, it looks like option B was the better deal, of course, by about 200 bucks there. So if the initial price was 18.5, which is the better option? That one right up there. And then I'm just curious if you happen to look at those and maybe extrapolate a little bit. Is this option better for any price of the car? Explain your reasoning. What do you think? If I put any initial value, any number in for x, would this one give me the lower value? Yeah, it would. Don't know if you kind of looked at this piece, but if you look at g composed of f of x, and if you were to simplify that, let's go ahead and bring in the 0.9. I end up getting 0.9x, and then I only get 90% of that rebate there, that 2,000, which would be 1,800. So if you kind of take a look there, I've got 0.9x minus 2,000. The other one is really just 0.9x minus 1,800. So obviously I'm subtracting more in option B than I am in option A. And so is this option better for any price of the car? Yeah, it is. And again, you're more than welcome to kind of write that out in some way there. I don't want to belabor the point on it. Okay, good. Just a good quick connection with composition of functions, just making sure we remind ourselves of some of the ideas we developed yesterday. Let's go ahead and try example 1 here. Just a couple linear functions, f of x and g of x. We're going to do a little composition both ways here, and watch what happens when we get our results. So f composed of g of x first. Let's go ahead and get them right away. So that just very simply means g of x, which is that right there, replaces the inputs of the f function. In this case, there's only one. So I have 3, and then 1/3 x plus 4, and then minus 4. All right. That's pretty nice right there. Let's see. In this case, obviously, multiplication comes before the subtraction. So let's do 3 times 1/3 times x plus 4. What do you guys happen to notice about the 3 times 1/3? Should just be 1, right? So I'm seeing this. Those kind of just cancel out, and you just get x plus 4 minus 4. And, well, the 4's then cancel out, and you end up getting x. So f composed of g of x is actually just x. Watch what happens when I switch it around. Let's reverse it here, of course. Let's do g composed of f of x. Let's see if I can fit this in. So that means f of x, which is this right here, replaces the inputs of the g function. In this case, there's only the one. So this goes in here. Let's see it play out. So 1/3, and then 3x minus 4, and then plus 4. All right, I hope that makes sense there. And in parentheses will probably come first before I can do the 1/3. So what do you notice in the minus 4 plus 4? They cancel out, and I get 1/3 times the 3x. And now it's just multiplication. 1/3 times 3 is just 1, so I just get, and lo and behold, 1x. So interesting. In each case, first of all, when I did the composition here, I got the same answer. And that answer is just really what we would call the original input. It's just x. Same here and same here. Now, I don't want to kind of go into this in too much detail because it is coming our way relatively soon. But these functions, the 3x minus 4 and the 1/3 x plus 4, do have a particular relationship. And if you look ahead in the next notes worksheet, you'll see maybe what they are called. But we'll take a look at it in the next section. So I'll just underline that piece and let's move on. All righty. Great. We know up to this point in time what we've done is we've taken two individual functions, combined them together with compositions to create a third function. Well, what I'm going to now do with this next set of problems is basically reverse the process. I'm going to start with the third function, and what I want us to do is come up with the original two functions that made it. So instead of composing, I'm decomposing a function. All righty. So this is the key right here, guys. Let's go ahead and box that up. So what I'm looking for is the original f of x and g of x so that its composition, and we'll just do this root, f composed of g of x, is equal to this piece over here. Now what I like about this type of problem is we can be a little creative with it. There are actually multiple answers here. Just as long as you can get the algebra to work, I'll definitely accept it. So I sort of think of this, and this is just my piece, is I sort of think of g of x as a function within a function. And so I look over here, and I've got a relatively basic function, square root of x plus 1. But can you sort of pull out or sort of identify a function within this overall function? Now I see one that's fairly obvious, at least to me. Maybe one secondarily, but I think I see this. If you look at this, isn't this just right here, this part of it, x plus 1? Isn't that kind of a function by itself? This would be a function within the larger function right up here. So that, guys, is going to be our g of x. Okay, so g of x, just one more time, I think of it as a function within the function. And I identify it, and I pull it out as that. Now, obviously, we know how compositions work. In this case, g of x replaces the input of the f function. So when I'm decomposing, whatever I pulled out, now I have to replace with an x because that's what g of x does. It replaces the input of the f function. So this now has to be your basic input. So instead of square root of x plus 1, I've pulled out the x plus 1, and f of x becomes square root of x. If I asked you to do a composition here, wouldn't you just take this x plus 1 and replace the input of the f function right there? Yeah. And that's how decomposition works. Now this one, it was a fairly basic function to start. So to me, there's really one that is most obvious in this case. I could probably think of a couple others, although not quite as good. But I think that's how we're going to play it out. Now examples 3 and 4 maybe are a little more complex, and so maybe we can get a little more creative with it. Okay, so I've got h of x equals 1 plus x squared, all raised to the third. And I guess I would ask you this. If you look at this function right here, can you sort of identify maybe a function within the larger function right here? Well, I'm going to play 1 out. So this would be one scenario. I see that 1 plus x squared, this piece, that's a function, right? So if I make g of x equal to 1 plus x squared, that is a function within the larger function, absolutely. Now remember how a composition plays out. G of x replaces the input of the f function. So whatever this is just gets replaced with your input. So I'm hoping you would see that this would have to be f of x right there. So whatever I take out, again, f of x is just going to be that as the input. And think of a composition here. Wouldn't this go in for x right here? And wouldn't that create this piece? Certainly. That's one option. I'm going to put a little curtain here and maybe just set up another one. How about just x squared? Isn't that a function? We've definitely seen the x squared as a function right there. So what if I created that as my g of x, the function within the function? What would f of x be if I pulled out x squared? Just remember the idea. Whatever you pull out has to be replaced with your basic input in the f function, and that's it. So instead of 1 plus x squared to the third, it's 1 plus x to the third, because x squared would replace right here. Again, there are probably a couple of others there, not quite as good, so I'm not going to introduce that idea out to you. I think those are two good ones, and either one I would certainly accept. If you have another one and you want to run it by me, please feel free to do that. All right, let's do example 4. Let's see if we can come up with at least 2 or 3 here. I'm sure we can come up with some. All right, I'm going to do one. I'm identifying a function within the function. It looks like I can create an absolute value function right there. How about that? Maybe have that be my g of x. So this piece, pull out as my function within the function. And remember, whatever I pull out, when I write my f of x function, just replace that with the basic input there. So how about 2x plus 5? So here's my absolute value function. This becomes a linear function. The composition, of course, creates this over here. So that's one. Maybe come up with another. Again, it's up to you. I'd love for you to be a little proactive on this. See if you can come up with some. How about pulling out just the x cubed minus 4? There we go. That looks kind of nice. Just pulling out that piece. And if I pull that out, again, whatever I pull out, I just put x for my f of x function. And so something like that would do. See the composition, everybody. By now, should really be clicking. Should be able to visualize one function replacing the input of another function. Let's come up with another one. How about maybe grabbing this part of it? So how about the 2 and the x cubed minus 4? Again, just all viable options here. And if I do that, what would the f of x function have to look like? And how does x plus 5 sound? This replaces that input, and I get the original right here. Pretty cool. If you come up with another one, please, again, feel free to run it by me. These are 3 great options right here. And again, I don't want to belabor the point. If you want to write a couple ideas down on how we got these, that's perfectly fine. Just to quickly summarize, remember g of x is sort of the function within the function. So I pull that out. And when I'm looking to write f of x, whatever I've pulled out, just go ahead and replace that with an input, just your basic x. And that's what I did in each case. All right, let's go get the last one. Example 5. A lakeside city whose economy depends largely on the lake is concerned about the presence of a certain pollutant, parts per million. Scientists have developed a model for the concentration in terms of the population. Okay, so concentration in terms of population, concentration in the output, population in the input. Looks like linear in nature here, I guess just for our ease purposes. In addition, the city government has developed a model for the population growth in terms of in terms of time. Okay, got it. Sorry, I just had to read through myself here. So population in terms of time. Yeah, this is the one that interestingly enough, is linear as opposed to maybe exponential or something, but that's fine. Again, just I think it'll be easy for us to work with this. So write a function for the concentration of the pollutant in terms of time. All right, so here's what we have. Concentration in terms of time. Output, input. So let's just kind of see the progression. If you want to do this in a different way, I'm not saying this is necessarily the ideal way to pull this off, but it just helps kind of make the connection to the composition here. So we start with time, and the question is, what quantity do I know if I know time? And just based on this connection right here, it looks like population from time. So I do have a function dealing with the population in terms of time. That looks great. And that population happens to be the input of this function right here, where that allows me to get the concentration. So again, that's kind of our connection. You can kind of see the piece of the puzzles come together. So time is the input, population is the output. This output becomes the input of this function right here, and now I can write concentration as a function of time. So I'm going to just do this piece. If you see it in a slightly different fashion, that's totally cool by me. But ultimately, I have time, and that means I can have population in terms of that time, so which is 1.47 t plus 27.8. Great. Now the idea is this is the population, and so that value replaces the input of the concentration function. So notice that is population, so it just goes right in there. So to get the concentration, and let me go ahead and do some arrows here just to separate, it looks like 2.54 times the population. Well, that population is this, so 1.47 t plus the 27.8, and then add that 98.55 on the back. And I think I mentioned this at the end of the previous lesson. You can definitely argue the point that composition is really nothing more than substitution. This substitutes in for that variable right there. Just to maybe save ourselves a little time and energy, I do have our function simplified on my paper, so I'm going to go ahead and do this. So this would be concentration in terms of time. And when you do simplify this, this would mean, of course, distributing this and then combining any like terms. I get this piece right here, so 3.7338 t, and I'm looking at 169.162. If you want to verify that, you are more than welcome to do that. But notice what we have, of course, the concentration, in terms of time, and that looks great. Awesome. What do you say we just go ahead and solve algebraically here one last piece, and then we'll wrap it on up. So scientists say that the pollutant concentration of 410 parts per million, and that's what it was in, parts per million, is harmful to vegetation and wildlife based on continuing trends. For how many years can the city expect no major problems? Alrighty, so we had our population in terms of time, concentration in terms of population. We combined two together to create the third, and we're looking for that concentration to be 410 is the breaking point. So let's throw 410 in place. Okay, so I've got 3.7338 t, add that 169 and change on the back end, and it's just an equation to solve for t. Alrighty. I'll go ahead and grab my calculator. So I hope everyone's cool with the two steps here. What do you say we subtract that on over and then divide by that 3.7 and change? So that should give us what we're looking for. So I've got 410. I'm going to take away the 169.162 and get that. And then divide by that 3.7338. If you could do the same, that would be excellent. And I've got that piece right there. Well, obviously, I'm sorry, I missed the one piece there. So the 240.838 didn't come up on the calculator. Then divide by that 3.7338. 338. That's much better. I think I added a 3 accidentally. Oh boy. There we go. Much, much nicer. So it looks like after about 64.5 years. Let's go with that and call it a winner. So about 64.5 years. All right, very nice. So just working with compositions over the last couple days. We'll continue working with those in the next lesson as well. But I think the 2-day lessons really work nicely with some of the problems you're going to see in the practice and the take-home quiz, etc. All righty. Well, if you have any questions, please don't hesitate to ask. Thanks.